Good morning. Welcome to our ICP DAS monthly webinar, Introduction to Serial Fieldbus and Industrial Ethernet. My name is Kathy Spinazi. I've been working as an application engineer for 27 years total, and for ICP DAS as an application engineer for 2.5 of those years. Previously, I also worked as a system design engineer in automation controls. The agenda this morning is as follows: traditional Fieldbus, the power of industrial Ethernet, efficiency gains, building a scalable network for future growth, case studies and real-world benefits, and addressing concerns and challenges. First, a little bit about ICP DAS. It was established in 1993, headquartered in Hsinchu, Taiwan. ICP DAS USA was launched in 2001. We have many certifications. We have fast service, free tech support, free software, fast shipping, warranty, and ROS compliant, ISO 9001 certified, and SGS. And we're a Windows embedded partner. Traditional Fieldbus utilizes serial two-way communication. It is digital. It is a bus that interconnects measurement and control equipment such as sensors, actuators, and controllers. It is a bus that devices can easily connect to. Before Fieldbus, computers were connected using serial RS-232 serial connections, by which only two devices could communicate. Fieldbus history. There was a definite need to move beyond two device connections. Many companies tackled the problem. One precursor to Fieldbus was General Purpose Interface Bus, or GPIB. In 1975, it became a standard for automation and industrial control. Its main application was for automated measurements, using instruments from many different manufacturers. It has a parallel bus of 24 wires and a maximum cable length of 20 meters. ArcNet was created in 1975, and it used a token mechanism. The device that had the token was allowed to initiate communication. When it finished, it would pass the token to the next device in order of node ID. Token networks have several disadvantages, including if the token fails, the entire network may stop working. A failed network card in one machine can also bring down the entire network segment, and it can be difficult to find the source of the disconnect. Token networks are generally slower than Ethernet networks, and data packets must pass through all nodes, which slows routing, and this can also lead to slower data transfer rates than other topologies like star or mesh. Performance can degrade as more nodes are added, or when the network is under heavy traffic. Each node must wait for its turn to transmit data, so the wait times increase as the number of nodes increases. In 1979, Modicon created a protocol called Modbus. They wanted to create a serial bus that would connect their PLCs programmable logic controllers. In its first version, Modbus used a 2-wire cable with EIA 485 UART signals. The protocol itself is very simple, with a master-slave protocol, and the number of data types are limited to those that were understood by PLCs at that time. Modbus, with its Modbus TCP version, is still one of the most used industrial networks, mainly in the building automation field. Manufacturing Automation Protocol, or MAP, was created by General Motors in 1982 for the interconnection of devices from multiple manufacturers. General Motors wanted to combat the incompatibility of devices from different manufacturers by getting them to use the protocol that they created. It was used for automation of manufacturing processes. By 1985, there were 21 different companies that offered MAP products. It was also a token bus type network and was slow compared with Ethernet. It did become an IEEE standard, but it was abandoned in 2004 because companies were moving towards faster Ethernet. Fieldbus was created by Intel in 1983, and it's the oldest, most commonly used Fieldbus technology. They separated slow I/O access from faster memory access. Fieldbus has one master node and multiple slaves, with the slaves only responding to requests from the master. It has 2 twisted pairs, one for data and the other for clocking and signals. It allows up to 250 nodes per segment with a total distance of 13.2 kilometers. PROFIBUS is another early Fieldbus protocol. PROFIBUS was created with the financial support of the German government in 1987. Initially, it was too complicated until Siemens created a modified application layer in 1994. After that, it became one of the most popular industrial protocols in the manufacturing industry. It has network diagnosis capability, exceptional performance, reliable data, flexible topology, expandability. It's compact and is easily maintained. Controller Area Network, or CAN, was created by the German company Robert Bosch GmbH in the 1980s to solve communication problems between different control systems in cars. The concept of CAN was that every device can be connected by a single set of wires, and every device that is connected can freely exchange data with any other device. CAN quickly became a part of the factory automation marketplace. DeviceNet was developed by Alan Bradley and is now maintained by the Open DeviceNet Vendor Association, or ODVA, as an open Fieldbus standard based on the CAN protocol. DeviceNet belongs to the family of Common Industrial Protocol, or CIP-based networks. CIP forms the common application layer of these 3 industrial networks: DeviceNet, ControlNet, Ethernet, IP. DeviceNet is an object-oriented bus system and operates according to the producer-consumer method. DeviceNet devices can be client, master, or server-slave, or both. Clients and servers can be producer or consumer, or both. CAN Open was developed by the manufacturing association called CIA, CAN in Automation. By the end of 2002, it was a standard for manufacturing automation in Europe. Today we have 2 categories of Fieldbus, and those are serial communication and industrial Ethernet communications. ICP DAS USA has products for each of those categories, both serial and industrial Ethernet Fieldbus. Serial Fieldbus protocols have been in use for years now. The technology is solid, and there are many vendors supporting it with a large variety of products that can be easily connected to, communicated with each other. Industrial Ethernet has also been around for years at this point and offers efficiency, high speed, plug-and-play devices with a choice of many vendors creating products, and there is easy scalability. The three main Fieldbus protocols over Ethernet are PROFINET, Ethernet IP, and Modbus TCP. Each have different areas of strength. Modbus TCP IP-based protocol is useful for non-time critical functions like energy consumption and environmental data collection. It's also used for data exchanges between field level and IT systems. PROFINET, high performance protocol for communications between PACs, PLCs, and I/O devices. It's suitable for real-time and safety-critical tasks like high-speed motion control. The reason for this is that it takes the TCP and UDP IP for communications that is not time-critical. For time-critical communication, it is able to bypass layers of communication, which gives it the necessary speed. Ethernet IP is used for real-time and safety-critical functions such as high-speed motion control. It is deterministic, high-performance protocol used for data exchange between controllers like PACs, programmable automation controllers, or PLCs, programmable logic controllers, and data acquisition devices. Given that each of the three field buses has a specific strength, all three are needed to give us the power of industrial Ethernet. Efficiency gains come from utilizing the strength of multiple kinds of field bus together to neutralize their individual weaknesses. An example of this is the automobile industry, where CAN is a network of choice because it's very noise tolerant due to its physical layer and protocol. It has non-destructive collision resolution and multicast and broadcast. It is two-wire and can run many feet. It has an inexpensive physical layer interface, but there are some disadvantages. The maximum data rate, if you use CAN FD, is between 8 and 10 megabits, which is slow in this day and age. As more devices in the car connect to the bus, it gets slower. To get around this problem, car manufacturers have added more CAN buses to the cars so that the load is distributed, keeping individual buses as fast as possible. But communicating between these many CAN between the many CAN buses, many are using ad hoc connections, which are not secure, thus leaving the car's systems open to cyber attacks. As cars are becoming increasingly more automated and electronic, using industrial Ethernet is a possibility to consider. The speed of industrial Ethernet protocols can go up into the gigabyte range. Although they are not as noise immune as CAN, and the physical layer is more expensive than CAN, many Ethernet components are hot pluggable, announcing themselves with boot P requests on power-up, making the system more easily scalable. Industrial Ethernet is more flexible in terms of handling the additional code and hardware needed for autonomous vehicles, GPS, and over-air updates and entertainment streaming. Combining with Ethernet Fieldbus for connecting the multiple CAN buses will allow for the addition of greater security of the Ethernet systems. Utilizing both serial Fieldbus and Ethernet Fieldbus together allow you to have the best of both. ICP DAS has converters and gateways that will allow you to convert from one Fieldbus type to another. The great thing about Fieldbus is it is very scalable. You can add more data acquisition modules, more controllers, more kinds of hardware, With the use of gateways and converters, you can use more than one Fieldbus protocol successfully, which opens up a variety of projects that you can do, from control of a factory floor to monitoring a fleet of electrical buses to controlling the aqua environment of a fish farm. One example of using serial Fieldbus in a local area is the Ashland National Forest area. It's located at an altitude of 2,216 meters above sea level and is Taiwan's most famous and popular forest recreation area. In order to protect the environment and achieve the goal of eco-friendly tours in the park's administration uses electric buses to provide transportation services in the recreation area. Since the Ashland National Forest Recreation Area is located at a high altitude with a very high level of humidity, factors such as terrain and weather can cause the following problems: lowering the mileage and battery lifespan of electric buses. Therefore, the control center hopes to effectively monitor the charging and aging process of batteries, driving distance, location, and the battery level of the electric buses. This case illustrates how a solution from ICP DAS for real-time fleet management is used to monitor and manage battery and traffic information of the electric buses in the Ashland area. For the Fieldbus portion of the system, we're using two of our Modbus RTU analog input modules. One is an 8-channel high-voltage analog input module, the M7017R A5G, to monitor the bus battery voltage, and an 8-channel thermocouple input module, the M7018RG, to monitor the battery's temperature. This information, along with the bus's location, is sent to the control center using a GTP 541M. The GTP 541 uses GPS and is for sale in Asia only because they have not been tested for emissions in this country. By sending data to the control center, if there is a problem with the bus, it can be quickly identified. The bus can be sent to a repair terminal if it breaks down and can be easily located for towing, and a replacement bus sent to the location for the pickup of passengers. There are many great options for HMIs. In this case, the data was pulled from the control room display where the technicians can monitor it, and the display was created using the M2M RTU API SDK. It could just as easily be created using Indusoft Web Studio or Viva Edge, which allows you to pull in maps from Google. Fieldbus and aquaculture. Fish production at the freshwater fish farms in Taiwan reached 259,175 tons in 2018, with an output value of up to $982 million, and this is according to the Taiwan government's fishery agency. However, extreme climate events have become increasingly frequent in recent years, including high temperatures, heat waves, short-term heavy rainfall, cold air masses, and other meteorological conditions. This has increased production risks in the aquaculture industry. In response to the energy management trend of energy efficiency and a reduction in the carbon footprint, as well as a reduction in industrial losses caused by natural disasters, the government has been encouraging fish farmers to utilize multiple forms of renewable energy, for example, solar energy or wind power. With the assistance of these new sources of energy, fish farmers are able to reduce their dependencies on traditional electric power. Additionally, the government is also motivating fish farmers to implement IoT technology and to build intelligent systems for smart farming, remote monitoring, and early warning. It can help the aquaculture industry to increase the ability to face production risks and to enhance production capacity and reduce production costs. Finally, the aquaculture is a step towards ensuring the sustainability of the fishing industry. Water quality sensors were set in the fish pond area to acquire data related to the water temperature, luminescence, oxidation reduction potential, ORP, dissolved oxygen, DO, electrical conductivity, EC, pH value, and NH4 ammonia, etc. A meteorological instrument was placed to acquire air pressure, luminescence and humidity, temperature, rainfall, wind direction, strength of sudden gusts, and wind speeds. With various sensors installed, they can acquire the data of power consumption as well as water information and meteorological information. With Modbus RTU Fieldbus devices like the TM P4C4 module and the TM DA1P1R1 module, and logic control from a VPD 173 are used in order to achieve the goal of smart farming. Zigbee modules like the ZT2551 and the ZT2550 send data to the TGW714 to be converted from Modbus RTU serial Fieldbus to Modbus TCP Ethernet Fieldbus. Data then goes to the control room where there is a PC running the Indusoft SCADA system. The HMI displays power consumption, water temperature, ammonia content, and water along with local weather conditions. Since the fish pond is at a large distance from the central control room, Zigbee wireless transmission and various I/O modules and communication converters were therefore employed so that we could integrate various equipment. The Turkcell data center in Ankara, the capital city of Turkey, is the nation's largest data center. It was built by the Turkcell Group. The data center provides services catering to Turkish companies and public institutions and international corporations. They're using Ethernet Fieldbus, Modbus TCP for communications. The data center houses numerous essential equipment systems, including servers, storage systems, network devices, switches, routers and firewalls, server racks, and cabling systems, etc. In the event of disasters or accidents, the crucial information is stored in the data center and it might be lost, resulting in huge losses. Therefore, strict environmental monitoring and access control in the data center is required. Prior to installing our equipment, the data center was monitored by numerous manual inspections of all hardware, and this was very time-consuming. This case study exemplifies how ICP DAS's Modbus TCP Fieldbus and environmental monitoring solutions accomplish monitoring multiple temperature and humidity measurement points and access control remotely. It's using one PET 7060 PoE Ethernet I/O module in each of the 8 server rooms. It's using to monitor and control the entrance at any time, as well as multiple DL100 EW remote temperature and humidity data loggers to obtain real-time data on environmental variables. The data collected is then transmitted to the control center over optical fibers subsequently. The management personnel can keep abreast of the server room's environmental conditions via the control center's SCADA system. When someone taps their card against the reader successfully, the PET 7060 receives a query from the control center to open the gate. Conversely, when access is denied, the door remains closed and the data is sent back to the control room center for activating alarm notifications. The system achieves access control very effectively. The DL100EW remote temperature and humidity data loggers measure the temperature, humidity, luminescence, and dew point of the environment. The data logger supports Modbus TCP and MQTT, enabling it to send temperature, humidity data to the SCADA system in the control center. Besides, the DL100EW only requires one Ethernet cable for data transmission and power supply. This saves on wiring efforts and installation costs and reduces maintenance costs over time, an advantage of PoE, Power over Ethernet. Modbus TCP Ethernet Fieldbus. Fire warning alarm systems are very important in saving lives and property from fires that happen all the time. Do you know the difference between a traditional alarm system and a linked fire alarm system from ICP DAS? If a fire is detected, the traditional fire alarm system will send an alarm to the control center to notify them where the fire has occurred. However, any occupants near the scene of the fire will not receive a notification, so they have no idea of the exact location of the fire. It can be said that they might not have enough information to identify the best escape route or to make the best decision regarding protecting their lives and property. In contrast, an intelligent linked fire alarm system made of ICP DAS WISE modules can be used to build a better solution for fire alarm applications. Looking at the image, when a fire is detected in Region F, the WISE 7152 module in Region F transmits an alarm via its advanced peer-to-peer function. All warning lights and alarms represented in Region F on the 6 WISE 7152 modules distributed in the 6 regions will be turned on to indicate a fire is occurring in Region F. Knowing the exact location of the fire can help guide personnel to a safe exit path so as to avoid the fire. After the fire in Region F has been put out, you just need to press the emergency switch to turn off the alarm. The alarm siren and warning lights on all of the WISE 7152 modules in all 6 sections will be turned off at the same time. A 7th WISE 7152 could be added to monitor the status of the 6 modules in case one is destroyed by fire or goes offline for another reason. The South Korean government started a project to install 300,000 electrical vehicle charging piles throughout South Korea. ICP DAS had an efficient solution using our intelligent CAN bridge. CAN to fiber and fiber to CAN protects the data from degradation due to electromagnetic noise over long distances, from the pile sites to the control center. At the control center, the PISO CAN 200UT PCI card handles the arbitration, error detections, and automatic error troubleshooting, as well as data retransmission. Having a central control system allows for efficient monitoring of all the charging stations without the need for thousands of people continually traveling to those station sites. Addressing concerns and challenges. Choosing the right version of Fieldbus for the application, for example, using CAN buses in cars for its noise immunity, and using PROFINET for real-time safety critical tasks at high-speed motion control. Learning the different field Fieldbus protocols for hardware that you want to use, because there are many different Fieldbus protocols, and learning each one that you want to use is an investment of time and money for education. Knowing multiple Fieldbus protocols does give you flexibility in being able to choose from a wide range of hardware from multiple manufacturers. Getting converters and gateways needed for all of your hardware communication together. That's one way ICP DAS USA can help. We've got many converters and gateways for signal and for serial and industrial Ethernet Fieldbus protocols. They can be easily configured, some through utilities and others through web pages. In summary, Fieldbus revolutionized the automation control industry by making it possible to create networks of various devices made by many different manufacturers that could all communicate together. These systems are easily scalable from a few devices to many in a system. Industrial Ethernet Fieldbus protocols added high speeds up to 1,000 megabits per second. They can also be used to transmit data without errors securely over long distances. Using Fieldbus to remotely log data can increase efficiency by removing the need for manual data recording at the remote sites. And using gateways and converters, you can utilize multiple different Fieldbus protocols in a single system. Anybody got any questions? If you want to get started with Fieldbus, feel free to contact us. Our phone number is 346-292-9998, and we will be happy to help you with any questions and any applications that you may have for utilizing Fieldbus and controlling whatever system you have. Thank you very much for attending our webinar, and have a great week. Bye-bye.